Tonight, we're going to embark on an exploration, one that truly reshapes how we understand our spot in the grand scheme of the cosmos. We'll delve into just how incredibly small our home world Earth truly is. And this isn't simply about comparing it to our local sun or the sprawling gas giant, Jupiter. This is about grasping the ultimate scale, the kind that effectively makes our planet vanish from any meaningful measure. Because there's a fundamental truth many people don't fully grasp: Earth isn't merely a small sphere. It exists as such an unbelievably tiny speck that articulating its true dimensions becomes an almost impossible task. As our journey concludes, you'll undoubtedly view our planet, and indeed yourself, through an entirely fresh lens. Let's begin right here, with Earth itself, the very ground beneath our feet, the world we inhabit each passing day. From our individual vantage point, standing here on its vast surface, Earth feels absolutely immense. One could easily dedicate an entire lifetime to travel, yet still fail to witness every single curve and corner of its magnificent expanse. The great continents stretch across thousands of miles, inviting endless exploration. Our deep oceans envelop roughly 71% of its surface, hiding mysteries within their depths. Towering peaks, like Mount Everest, ascend nearly 30,000 feet into the crisp, upper atmosphere, touching the very edge of the breathable air. For the earliest human civilizations, this planet was everything. It represented the entire known universe. The sky above was perceived as nothing more than a solid dome adorned with twinkling lights. The ground beneath seemed flat, extending infinitely in every direction they could perceive. This perspective made perfect sense, based purely on what their eyes could take in. When you gaze toward the distant horizon, the land does indeed appear level and unending. The subtle curvature of our globe is simply too vast, too gentle to be noticed, without ascending to significant heights. Our planet has an equatorial diameter measuring approximately 7,926 miles. If, hypothetically, someone wished to walk along the equator, possessing the remarkable ability to traverse oceans, they would cover a distance of about 25,000 miles. Maintaining a consistent pace of 3 miles per hour and walking for 8 hours each day, this incredible trek would span roughly 3 years and 1 month. That's an astonishingly long journey, a testament to Earth's considerable size from a human perspective. The total surface area of our world is approximately 197 million square miles. To truly appreciate this magnitude, imagine attempting to visit every single square mile, spending just 1 second at each unique location. This continuous endeavor would consume over 6 years of your life. Even a country as large as the United States, one of the biggest nations on Earth, encompasses only about 3.8 million square miles. This represents less than 2% of our planet's entire surface. However, this is where our understanding begins to subtly shift. When we simply pull back, zooming out just a little, and start comparing Earth to other celestial bodies in the vastness of space, its perceived grandeur begins to diminish. Not in any physical sense, of course, but in its overall significance. Our planet ceases to be the absolute everything and transforms into merely one object among countless others. And as we continue to expand our view, pulling back further and further, it becomes progressively smaller, until it reaches a point where it's almost impossible to even discern. Our initial step on this cosmic expedition takes us to our closest celestial companion, the Moon. This familiar orb orbits our planet at an average distance of about 8,855 miles. To put this into perspective, that's roughly the same distance you would cover if you drove around Earth's equator 9.5 times. It certainly sounds like a considerable distance, and it unquestionably is, by any human standard. When the brave Apollo astronauts made their historic journey to the moon, it took their spacecraft approximately 3 days to complete the trip. The moon itself possesses a diameter of roughly 2,159 miles. This measurement makes it about 27% of Earth's diameter. So, while our moon is indeed smaller than our planet, the difference isn't dramatically pronounced. If we were to imagine Earth as the size of a standard basketball, then our moon would be comparable to a tennis ball situated nearby. Yet, here's an intriguing aspect that often goes unnoticed. The actual distance separating Earth and the moon is approximately 30 times Earth's own diameter. Picture, if you will, aligning 30 Earth-sized spheres, one after the other, in a continuous line between our world and its lunar companion. That immense amount of vacant space exists within that seemingly short gap. Most individuals don't fully realize this vast emptiness. When you encounter images depicting Earth and the moon together, they are almost invariably shown much closer than their actual astronomical separation. The reality reveals an enormous expanse of nothingness existing between us and our nearest celestial neighbor. This provides our very first clue that the universe is overwhelmingly composed of empty space. Even within our immediate cosmic vicinity, the distances involved are colossal, especially when weighed against the actual sizes of the objects themselves. The unique relationship between the moon and Earth is actually quite distinct within our solar system. The majority of moons found orbiting other planets are typically minuscule in comparison to their parent bodies. However, our own moon is remarkably substantial relative to Earth. In fact, the Earth-Moon system is occasionally referred to as a double planet, due to the moon's significant size in proportion to its primary. The moon's considerable mass exerts tangible effects upon Earth. It is the gravitational pull of the moon that generates the ocean tides we observe and experience daily across our planet. Furthermore, the moon plays a crucial role in stabilizing Earth's axial tilt. Without its steadying influence, Earth's rotational axis might experience dramatic wobbles over extended periods. Such instability could lead to extreme and unpredictable climate variations, potentially rendering the development or sustained existence of complex life incredibly difficult, if not entirely impossible. Observing the moon from Earth, it appears to occupy roughly the same visual size in our sky as the sun. This striking phenomenon is a complete cosmic happenstance. The sun is, in reality, approximately 400 times larger in diameter than the moon. However, it is also situated about 400 times farther away from us. This precise alignment and distance ratio creates the breathtaking spectacle of total solar eclipses, where the moon perfectly obscures the sun's disk. Our lunar companion is also gradually receding from Earth. Each year, it drifts away by about 1.5 inches. This slow, ongoing separation is a consequence of tidal interactions between our two bodies. Billions of years ago, the moon was considerably closer to Earth, and a single day on our planet was much shorter, perhaps lasting only around 5 hours. For the foreseeable future, however, the moon will persist as our closest and most familiar celestial partner in space. In 1969, humanity achieved a monumental milestone when individuals first set foot upon its surface, a defining moment that showcased the extraordinary capabilities we possess when we push the boundaries of human endeavor and scientific exploration. Now, let us turn our attention to the sun, our star. The sun is the fundamental reason for our very existence. Without its ceaseless outpouring of light and heat, Earth would simply be a desolate, frozen rock, hurtling through the frigid vacuum of space. Yet, it is in comparison to the sun that Earth's dimensions truly begin to pale, shrinking into near insignificance. Our sun possesses an immense diameter of approximately 864,000 miles. This makes it a staggering 109 times wider than Earth. The Sun's sheer volume is so colossal that an estimated 1.3 million Earth-sized worlds could comfortably fit within its vast interior. Take a moment to truly ponder that figure. Every single mountain peak, every expansive ocean, every bustling city, every individual who has ever drawn breath on this planet, all of human history and experience, has unfolded on a world whose entire volume represents less than 1/1,000,000th of the Sun's internal space. The Sun holds an overwhelming 99.86% of all the mass present within our entire solar system. Everything else, all the planets, their moons, the myriad asteroids, and the countless comets combined, accounts for a mere 0.14% of the total mass. Our star is also situated approximately 93 million miles away from Earth. This monumental distance is formally designated as 1 astronomical unit, or AU. Light, traveling at its incredible speed, takes roughly 8 minutes and 20 seconds to bridge this gap and reach our planet. If, by some impossible cosmic event, the Sun were to suddenly vanish, we would remain completely unaware of its disappearance for over 8 minutes, because the light carrying the news of its absence would still be traveling toward us across that immense void. To fully grasp this incredible distance, imagine a vehicle maintaining typical highway speeds. Such a vehicle would require an astonishing 176 years of continuous travel to traverse this 93-million-mile gulf. Even the fastest spacecraft ever constructed by humans, the Parker Solar Probe, still takes months to reach its closest approach to the Sun, despite achieving velocities exceeding 400,000 miles per hour at its perihelion. Despite its overwhelming dominance in our sky, the Sun is actually considered a rather ordinary star within the cosmic context. Astronomers categorize it as a G-type main sequence star, often colloquially termed a yellow dwarf. It is currently estimated to be about 4.6 billion years old, placing it comfortably in its middle age. Our Sun holds sufficient hydrogen fuel within its core to continue burning steadily for another 5 billion years or so before it begins its eventual transition into a dying star. The sheer power emanating from the Sun is truly staggering. Every single second, it converts approximately 600 million tons of hydrogen into helium through a process known as nuclear fusion. This incredibly efficient reaction unleashes an incomprehensible amount of energy. The Sun generates more energy in a mere single second than all of human civilization has managed to produce throughout its entire recorded history. The visible surface of the Sun, known as the photosphere, maintains a temperature of around 10,000 degrees Fahrenheit. Deep within its core, however, where the intense nuclear fusion reactions occur, temperatures soar to an incredible 27 million degrees Fahrenheit. The pressure exerted at this core is approximately 260 billion times greater than Earth's atmospheric pressure at sea level. The Sun also periodically unleashes powerful solar flares and coronal mass ejections, or CMEs. These are colossal releases of energy and vast quantities of matter from the Sun's outer atmosphere. When these energetic phenomena are directed toward Earth, they can produce spectacular auroras, shimmering displays of light near our planet's polar regions. However, they also possess the potential to disrupt crucial satellite operations, destabilize electrical power grids, and interfere with global communication systems. Observing the Sun and understanding its true scale, and when we really look at the Sun, it reminds us that Earth doesn't actually sit at the center of our cosmic home. For much of human history, people firmly believed that our planet was the absolute core of everything. It took the brilliant insights of thinkers like Nicolaus Copernicus and Galileo Galilei to demonstrate that the Sun actually held the central position, with Earth simply orbiting around it. This realization served as humanity's very first significant lesson in cosmic humility. Our solar system stretches out much further than just Earth and the Sun. Let's pull back even more and see where our little planet fits into this much grander arrangement. The inner solar system is where we find the rocky, terrestrial worlds. Closest to our star is Mercury, perpetually baked by intense heat and then plunged into extreme cold during its long nights. Next, we encounter Venus, shrouded perpetually in its dense, toxic atmosphere. Then comes our own world Earth, a vibrant blue marble, positioned at what seems to be just the right distance for liquid water to exist. Finally, Mars completes this quartet of inner planets, a stark, frigid desert that, long ago, might have hosted flowing rivers. These four solid worlds huddle relatively close to our guiding star, all residing within about 1.5 times Earth's orbital distance from the Sun. Beyond Mars, a vast expanse opens up, populated by the asteroid belt. This expansive region contains countless rocky fragments, essentially the leftover building blocks that never quite managed to coalesce into a full-fledged planet. The largest of these objects, Ceres, measures only about 580 miles across. To give you an idea, more than 13 objects the size of Ceres could be lined up side by side across Earth's diameter. Despite the sheer number of millions of objects it contains, the asteroid belt is predominantly empty space. If you were to somehow navigate a spacecraft through it, you would likely never actually see an asteroid with your unaided eye. The immense distances separating these small bodies utterly dwarf their individual sizes. Then, we transition into the domain of the true giants. Jupiter stands as the undisputed king of the outer solar system, observing its realm with immense gravitational authority. With a colossal diameter of approximately 6,881 miles, it spans about 11 times the width of Earth. Jupiter's sheer volume is so overwhelming that 1,321 Earth-sized worlds could barely fill its interior. This planet is enormous, defying easy mental visualization. It holds more mass than all the other planets in our solar system combined. If Jupiter were a hollow sphere, you could literally place every other planet within our solar system inside it, with plenty of room still remaining. And yet, even this behemoth, Jupiter itself, is still tiny when compared to the Sun. Roughly 1,000 Jupiters could fit within the Sun's immense volume. Saturn follows Jupiter in the outer reaches of our solar system, nearly as awe-inspiring in its scale. With a diameter of about 2,367 miles, Saturn could comfortably contain 764 Earth-sized worlds within its massive bulk. But Saturn's most distinctive and famous feature isn't its size. It's the absolutely magnificent ring system that elegantly encircles it. Composed of untold billions of particles of ice and rock, these rings extend for tens of thousands of miles from the planet's cloud tops. Despite their vast span, they are astonishingly thin. If you were to hypothetically reduce Saturn to the size of a basketball, its glorious rings would be thinner than a single sheet of paper. Further out, in the cold, dark expanse beyond Saturn's orbit, dwell the ice giants Uranus and Neptune. Both are smaller than their gas giant predecessors, Jupiter and Saturn, but they still unequivocally dwarf Earth. The total volume of Uranus is equivalent to roughly 63 planets the size of ours. Meanwhile, Neptune's deep interior could comfortably accommodate 57 bodies with the mass of Earth. These incredibly distant worlds take decades, or even centuries, to complete just a single orbit around our Sun. Neptune, holding the record as the most distant recognized planet, requires a staggering 165 Earth years just to make one full trip around our star. Beyond the orbit of the known planets lies the Kuiper Belt, an extensive region that stretches from Neptune's path outwards for billions of miles. This vast area is densely populated with icy bodies, remnants from the very formation of our solar system. Pluto, once revered as our ninth planet, resides here among thousands of similar frozen worlds. Pluto itself measures only about 1,473 miles across. Roughly 5.4 Plutos could be lined up side by side across Earth's diameter. The Kuiper Belt represents a colossal reservoir of primordial ice, acting as a frozen archive of the raw materials from which our solar system was born. But even the Kuiper Belt does not mark the true, outermost edge of our solar system. Far, far beyond, at distances almost incomprehensibly vast, lies the Oort cloud. This immense, spherical shell, composed of billions of icy objects, envelopes our entire solar system like a colossal cosmic bubble. It begins at approximately 2,000 times Earth's distance from the Sun and extends outwards to nearly 2 light-years. To put that in perspective, that's almost halfway to the nearest star beyond our own. Objects residing in the Oort cloud are so incredibly distant that they are barely affected by the Sun's gravitational pull. They are more akin to loosely held prisoners than objects firmly bound in orbit. No human eye has ever directly observed an Oort cloud object. We deduce its existence only because comets occasionally begin a long, slow fall inward from this incredibly remote realm, their icy surfaces vaporizing into spectacular tails as they approach the warming influence of the Sun. The fundamental point here is clear. Our solar system is incredibly, astonishingly vast. It extends for trillions of miles in every direction, and within this immense volume, Earth is merely one small, rocky planet, gracefully orbiting at a distance that, in the grand scheme of things, is relatively close to our Sun. If we were to construct a proportional model where our Sun was represented by the diameter of a basketball, then Earth would be no larger than a peppercorn, positioned at a distance of 26 feet away. You would require an entire football field just to adequately illustrate the orbit of Neptune at this specific scale. Let's dive a little deeper into each of these worlds now, to really emphasize how tiny Earth truly is within our immediate planetary neighborhood. Mercury, the planet closest to the intense heat of the Sun, is a small, incredibly dense world, its surface heavily pockmarked with craters. It possesses almost no atmosphere, meaning there's absolutely nothing to shield it from the constant barrage of meteorite impacts, or to trap any heat. Mercury's surface endures astonishing temperature fluctuations, soaring beyond 1,000 degrees Fahrenheit under direct sunlight, and plummeting to a frigid -290 degrees in the utter darkness of its night side. Our Earth's atmosphere, by contrast, acts as a vital protective blanket, shielding us from such extreme variations. Our planet's temperature swings are minuscule when compared to Mercury's. Mercury completes one orbit around the Sun in just 88 Earth days, but it rotates on its axis at an incredibly slow pace. A single day on Mercury, measured from one sunrise to the next, actually lasts for 176 Earth days. This remarkable fact means that one Mercurian day is, in essence, longer than one Mercurian year. Imagine living on a world where a single cycle of daylight and darkness outlasts an entire orbital period around its star. The very concept of time would be experienced in a fundamentally different way. This perspective, truly humbling. This constant push outward from the Sun, this incredible outpouring of energy, reminds us that our small planet isn't the central point of the entire solar system. For most of human history, people genuinely believed Earth was the absolute core of everything. It took the revolutionary ideas of brilliant minds like Nicolaus Copernicus and Galileo Galilei to ultimately demonstrate that the Sun held the central position and our world merely orbited it. This revelation was humanity's very first, profound lesson in cosmic humility. Our solar system stretches far, far beyond just Earth and its star. Let's zoom out further and observe Earth's place within this much larger structure. The inner solar system is where we find the rocky, terrestrial planets. Mercury hugs closest to the Sun, a world alternately scorched and frozen in its extreme orbital dance. Venus follows, perpetually shrouded in its thick, toxic atmosphere. Then comes Earth, our vibrant blue marble, orbiting at what seems to be a perfectly balanced distance for liquid water to exist. Mars rounds out these inner worlds, a cold, dusty desert that, long ago, probably hosted flowing rivers. These 4 solid planets cluster relatively close to our star, all of them situated within about 1.5 times Earth's orbital distance from the Sun. Between Mars and the next giant planet lies a massive gap, filled with the asteroid belt. This expansive region contains countless rocky fragments, essentially the leftover building blocks that never quite managed to coalesce into a full-fledged planet. The largest of these objects, Ceres, measures only about 580 miles across. To give you an idea of scale, more than 13 objects the size of Ceres could be lined up side by side across Earth's diameter. Despite the millions of objects it contains, the asteroid belt is predominantly empty space. If you were to somehow fly a spacecraft through it, you would almost certainly never see an asteroid with your unaided eye. The distances separating these small bodies are enormous, completely dwarfing their individual sizes. Then, we enter the realm of true giants. Jupiter dominates the outer solar system, a colossal king surveying its vast domain. With an incredible diameter of approximately 6,881 miles, it's about 11 times wider than Earth. Jupiter's volume is so immense that 1,321 Earth-sized worlds could barely fill its interior. This planet is massive beyond any easy comprehension. It contains more mass than all the other planets in our solar system combined. If Jupiter were a hollow sphere, you could literally fit every other planet in the solar system inside it, with plenty of room still to spare. And yet, even Jupiter itself is tiny compared to the Sun. Roughly 1,000 Jupiters could fit within the Sun's immense volume. Saturn follows Jupiter in the outer solar system, nearly as impressive in its sheer scale. With a diameter of about 72,367 miles, Saturn could comfortably swallow 764 Earth-sized worlds within its vast bulk. But Saturn's most distinctive feature isn't its size. It's the truly magnificent ring system that gracefully encircles it. Made of countless particles of ice and rock, these rings extend for tens of thousands of miles from the planet's cloud tops. Yet, they are remarkably, astonishingly thin. If you were to imagine scaling Saturn down to the size of a basketball, its rings would be thinner than a single piece of paper. The ice giants, Uranus and Neptune, dwell in the deep, cold darkness beyond Saturn's orbit. Both are smaller than Jupiter and Saturn, but they still unequivocally dwarf Earth. The total volume of Uranus is roughly equivalent to 63 planets the size of ours. Meanwhile, Neptune's deep interior could comfortably accommodate 57 bodies with the mass of Earth. These incredibly distant worlds take decades, or even centuries, to complete just one single orbit around the Sun. Neptune, holding the record as the most distant recognized planet, requires a staggering 165 Earth years just to make one full trip around our star. Beyond the orbits of the known planets lies the Kuiper Belt, an expansive region stretching from Neptune's path outwards for billions of miles. This vast area is filled with icy bodies, remnants from the very formation of our solar system. Pluto, once revered as our 9th planet, resides here among thousands of similar frozen worlds. Pluto itself measures only about 1,473 miles across. Roughly 5.4 Plutos could be lined up side by side across Earth's diameter. The Kuiper Belt represents a colossal reservoir of primordial ice, acting as a frozen archive of the raw materials from which our solar system was born. But even the Kuiper belt does not mark the true, outermost edge of our solar system. Far, far beyond, at distances almost incomprehensibly vast, lies the Oort cloud. This immense, spherical shell, composed of billions of icy objects, completely surrounds our solar system like a colossal cosmic bubble. It begins at approximately 2,000 times Earth's distance from the Sun and extends outwards to nearly 2 light-years. To put that in perspective, that's almost halfway to the nearest star beyond our own. Objects residing in the Oort cloud are so incredibly distant that they are barely affected by the Sun's gravitational pull. They are more akin to loosely held prisoners than objects firmly bound in orbit. No human eye has ever directly observed an Oort cloud object. We deduce its existence only because comets occasionally begin a long, slow fall inward from this incredibly remote realm, their icy surfaces vaporizing into spectacular tails as they approach the warming influence of the Sun. The fundamental point here is clear. Our solar system is incredibly, astonishingly vast. It extends for trillions of miles in every direction. And within all that immense space, Earth is merely one small, rocky planet, gracefully orbiting at a distance that, in the grand scheme of things, is relatively close to our Sun. If we were to construct a proportional model where our Sun was represented by the diameter of a basketball, then Earth would be no larger than a peppercorn, positioned at a distance of 6 feet away. You would require an entire football field just to adequately illustrate the orbit of Neptune at this specific scale. Let's delve a little deeper into each of these inner worlds now, to really emphasize how small Earth truly is within our immediate planetary neighborhood. Mercury, the planet closest to the intense heat of the Sun, is a small, incredibly dense world, its surface heavily pockmarked with craters. It possesses almost no atmosphere, meaning there's absolutely nothing to shield it from the constant barrage of meteorite impacts or to trap any heat. Mercury's surface endures astonishing temperature fluctuations, soaring beyond 800 degrees Fahrenheit under direct sunlight, and plummeting to a frigid -290 degrees in the utter darkness of its night side. Our Earth's atmosphere, by contrast, acts as a vital protective blanket, shielding us from such extreme variations. Our planet's temperature swings are minuscule when compared to Mercury's. Mercury completes one orbit around the Sun in just 88 Earth days, but it rotates on its axis at an incredibly slow pace. A single day on Mercury, measured from one sunrise to the next, actually lasts for 176 Earth days. This remarkable fact means that one Mercurian day is, in essence, longer than one Mercurian year. Imagine living on a world where a single cycle of daylight and darkness outlasts an entire orbital period around its star. The very concept of time would be experienced in a fundamentally different way. Venus is sometimes referred to as Earth's twin planet, primarily because of its very similar size, but the resemblances end there quite abruptly. Venus boasts an incredibly thick atmosphere, composed primarily of carbon dioxide, with dense, swirling clouds of sulfuric acid. This atmosphere is so exceptionally thick that the surface pressure is about 90 times higher than Earth's. That's equivalent to the crushing pressure you would experience if you were 3,000 feet underwater in Earth's deepest oceans. The greenhouse effect on Venus is absolutely extreme. Venus maintains a relentless, uniform temperature of 900 degrees Fahrenheit across its entire surface, a direct result of carbon dioxide's runaway greenhouse effect. This temperature is hot enough to liquefy lead. Venus is, in fact, hotter than Mercury, despite being located farther away from the Sun. This serves as a stark example of what can occur when a greenhouse effect spirals completely out of control. It stands as a powerful cautionary tale for our own planet Earth. Venus also rotates in a backward direction compared to the majority of other planets in our solar system. While Earth and most other planets spin counterclockwise when viewed from above their north pole, Venus rotates clockwise. Scientists still aren't entirely sure why this anomaly exists. It's possible that, very early in the solar system's history, the planet was struck by a massive object that literally knocked it over, reversing its spin. Venus also rotates very, very slowly. One full rotation on Venus takes an astonishing 243 Earth days. When combined with its orbital period around the Sun, this means that the Sun actually rises in the west on Venus and sets in the east. Mars is smaller than Earth, but in many respects, it shares more similarities with our planet than Venus does. Mars possesses polar ice caps, which are composed of both water ice and frozen carbon dioxide. It also experiences seasons, though they are roughly twice as long as Earth's. Primarily because Mars takes approximately 687 Earth days to complete one orbit around the Sun. Mars once clearly had liquid water flowing on its surface. Ancient riverbeds and distinct lakebeds are readily visible in images captured by Mars orbiters and rovers, providing compelling evidence of a watery past. However, something dramatic happened to Mars. It lost the vast majority of its atmosphere. Without a thick, protective atmospheric blanket, liquid water cannot persist on the surface. It either freezes solid or rapidly evaporates into the thin air. Today, Mars averages a brutally cold -80 degrees Fahrenheit. Although equatorial summers can occasionally reach just above freezing, polar winters plunge far deeper into frigid temperatures. The atmosphere is so incredibly thin that the surface pressure is less than 1% of Earth's. Why did Mars lose its atmosphere? The planet is smaller than Earth, so its gravitational pull is inherently weaker. But the primary reason is that Mars lost its global magnetic field. Earth's magnetic field is generated by the swirling motion of molten iron within our planet's core. This powerful field acts like an invisible shield, deflecting the solar wind, a relentless stream of charged particles constantly emanating from the Sun. Mars once possessed a magnetic field, but its core cooled and eventually solidified, effectively shutting down the protective field. Without this crucial defense, the solar wind slowly but surely stripped away Mars's atmosphere over hundreds of millions of years. Mars has two small, irregularly shaped moons, Phobos and Deimos. Phobos is only about 14 miles across. It orbits so incredibly close to Mars that it completes 3 full revolutions around the planet during each Martian day. Phobos is also gradually spiraling inward. In approximately 50 million years, it will either violently crash into Mars or be torn apart by intense tidal forces, eventually forming a temporary ring around the planet. The asteroid belt, as we discussed, sits between Mars and Jupiter. It contains millions of rocky objects, but the total combined mass of all asteroids in this belt is less than 4% of the Moon's mass. If you were somehow flying through the asteroid belt, you wouldn't see asteroids densely packed everywhere like in science fiction movies. The distances between them are enormous. You would actually have to aim very carefully to even hit one. Ceres, the largest object within the asteroid belt, is particularly interesting. It's spherical, shaped by its own gravity, which is why it's classified as a dwarf planet. Ceres has a diameter of about 588 miles, roughly the width of Texas. NASA's Dawn spacecraft visited Ceres from 2015 to 2018 and found compelling evidence of a subsurface ocean. Ceres might actually contain more fresh water than all of Earth's lakes and rivers combined. Jupiter, as we know, dominates the outer solar system. It's so incredibly massive that its immense gravity influences the orbits of comets and asteroids throughout the entire solar system. Jupiter effectively acts like a cosmic vacuum cleaner, attracting and capturing many objects that might otherwise pose a threat to the inner planets. Some scientists believe Jupiter's presence has been absolutely crucial for Earth's development, significantly reducing the number of large impacts our planet experienced. It's possible that Jupiter's gravitational shield made it feasible for complex life to evolve here. Jupiter's most famous feature is undoubtedly the Great Red Spot, a colossal storm, larger than Earth itself, that has been raging continuously for at least 400 years. Wind speeds at the edges of this incredible storm can reach approximately 400 miles per hour. The storm is, however, slowly diminishing in size. A century ago, it was about 3 times wider than Earth. Now it's only about 1.3 times wider. If this shrinking trend continues, the Great Red Spot might entirely disappear within our own lifetimes. Jupiter has at least 95 known moons, and more are regularly being discovered as our telescopic technology continues to improve. The 4 largest moons, collectively known as the Galilean moons, after Galileo, who first observed them, are individual worlds in their own right. Io is the most volcanically active body in the entire solar system. Its surface is constantly being reshaped and resurfaced by a continuous barrage of volcanic eruptions. Europa has a remarkably smooth, icy surface, crisscrossed with intricate cracks. Beneath this icy shell, there is very likely a global ocean that could contain twice as much water as all of Earth's oceans combined, making it a prime target in the search for extraterrestrial life. Ganymede is the largest moon in the entire solar system, even surpassing the planet Mercury in size. And Callisto is heavily cratered, preserving one of the oldest and most pristine surfaces in the solar system, a testament to its ancient history. Saturn is arguably the most visually stunning planet, thanks to its breathtakingly beautiful and intricate ring system. These rings are composed of countless particles of ice and rock, ranging in size from microscopic grains to boulders as large as houses. The rings extend from about 4,300 miles to about 75,000 miles above Saturn's cloud tops. Yet, as we mentioned, they are remarkably thin, in most places only about 30 feet thick. Scientists are still uncertain about the precise age of Saturn's rings. They might have formed concurrently with Saturn itself, some 4.6 billion years ago. Alternatively, they could be much younger, perhaps only a few 100 million years old, having formed when a moon was tragically torn apart by Saturn's immense gravitational forces. This remains an active area of scientific debate. Saturn has at least 146 known moons, making it the planet with the most known satellites in our solar system. The largest of these, Titan, is bigger than Mercury. Titan holds the unique distinction of being the only moon in the solar system with a thick atmosphere. In fact, Titan's atmosphere is even denser than Earth's. The surface pressure there is about 1.5 times Earth's sea level pressure. Titan's atmosphere is primarily nitrogen, similar to Earth's, but it also contains significant amounts of methane. Titan also has liquid on its surface, but it's not water. It's far too cold for liquid water to exist there. Instead, Titan boasts lakes and seas of liquid methane and ethane. These hydrocarbon liquids rain from the sky, carve intricate river channels, and collect in low-lying areas. Titan is the only place in the solar system, besides Earth, where we have definitively confirmed stable bodies of surface liquid. Another incredibly fascinating moon in Saturn's system is Enceladus. This small moon, only about 313 miles across, has active geysers at its south pole that blast plumes of water ice hundreds of miles into space. This water originates from a subsurface ocean. The Cassini spacecraft actually flew directly through these geysers and detected organic molecules, which are the fundamental building blocks of life. Enceladus is now considered one of the most promising locations in our solar system to actively search for extraterrestrial life. Uranus is quite unusual because it's dramatically tilted on its side. Its axis of rotation is tilted by about 98 degrees from the vertical. This extreme tilt means that during parts of its long orbit, one of its poles points almost directly toward the Sun, experiencing continuous sunlight for 42 Earth years. During its winter, that same pole experiences continuous darkness for 42 years. The planet's equator, meanwhile, maintains more typical day and night cycles. Scientists still don't fully understand why Uranus is tilted so dramatically. The most plausible explanation suggests that very early in the solar system's tumultuous history, the planet was struck by a massive object that literally knocked it over. This colossal collision might also explain why its magnetic field is unusually tilted and offset from the planet's physical center. Neptune is the farthest recognized planet from the Sun. It's so incredibly distant that it takes approximately 165 Earth years to complete just one single orbit. The planet was discovered in 1846, meaning it has completed less than 2 full orbits around our star since we first observed it. Wind speeds on this incredibly remote world reach up to an astonishing 1,200 miles per hour, making them the fastest sustained winds measured on any planet in the solar system. These extreme winds generate vast storm systems, similar in nature to Jupiter's Great Red Spot. Voyager 2 observed a prominent storm called the Great Dark Spot in 1989. However, when the Hubble Space Telescope later examined the planet in 1994, the Great Dark Spot had completely vanished, and new storm systems had formed in its place. The weather on Neptune changes quickly and unpredictably. At least 16 known moons orbit this distant ice giant. The largest, Triton, is unusual because it orbits backward, or in retrograde motion, compared to the planet's rotation. This retrograde orbit strongly suggests that Triton did not form alongside its parent world, but was instead gravitationally captured from the Kuiper belt. This moon, too, is slowly spiraling inward. In approximately 3.5 billion years, it will either crash into Neptune or be torn apart by tidal forces, eventually forming a temporary ring system around the distant world. Beyond Neptune, as we've mentioned, lies the Kuiper belt, a vast region populated by icy bodies, remnants from the solar system's early formation. Pluto is the most famous object in the Kuiper belt. It was considered the 9th planet from its discovery in 1930 until 2006, when astronomers re-evaluated and redefined what constitutes a planet. Pluto didn't meet the new criteria because it hasn't gravitationally cleared its orbit of other debris. Pluto is small, only about 1,473 miles across. But it's a fascinating world. It has 5 known moons, the largest being Charon, which is about half Pluto's size. Pluto and Charon are so close in size that they are sometimes referred to as a binary system. They actually orbit a point in space between them, rather than Charon simply orbiting Pluto. NASA's New Horizons spacecraft flew past Pluto in July 2015, providing us with our first close-up views. The images revealed a complex world with mountains made of water ice, vast plains of frozen nitrogen, and a thin, hazy atmosphere that extends much farther than scientists had initially expected. Pluto even has a large, heart-shaped region known as Tombaugh Regio, named after Clyde Tombaugh, who discovered Pluto in 1930. There are other substantial Kuiper belt objects. Eris, Makemake, and Haumea are all classified as dwarf planets. These objects reveal that the outer solar system is far more populated than we once thought. There might be thousands of dwarf planets in the Kuiper belt, though most are too small and too faint to detect with our current telescopes. Beyond the Kuiper belt is the Oort cloud. While no object in the Oort cloud has ever been directly observed, we know it exists because of comets. Long-period comets, those that take hundreds or thousands of years to orbit the Sun, originate from the Oort cloud. When the gravity of a passing star disturbs an Oort cloud object, it can begin to fall toward the inner solar system, eventually becoming a visible comet. The Oort cloud is truly enormous. It extends from about 2,000 astronomical units, AU, to 100,000 AU from the Sun. That's nearly 2 light-years. The Oort cloud is so incredibly far away that the Sun's gravity barely holds onto its contents. A strong gravitational disturbance could easily pull objects completely free from the solar system's grasp. This incredibly vast region marks the true, outermost boundary of our solar system. Beyond the Oort cloud, the Sun's gravitational influence becomes negligible. Space then transitions into the interstellar realm, the immense void between stars. And in all this vast volume, Earth is one small rocky planet, 8,000 miles across, orbiting 1.0 AU from the Sun. The solar system extends for trillions of miles, and our Earth occupies only a tiny, tiny fraction of that space. Now, let's leave the confines of our solar system and venture out into the space between the stars. This is where distances become so monumentally large that our familiar measurements simply cease to make practical sense. The closest star to our Sun is Proxima Centauri, a component of the Alpha Centauri system. It's situated about 4.24 light-years away. A light-year, for reference, is the distance that light travels in 1 Earth year, which equates to approximately 5.88 trillion miles. So, Proxima Centauri is roughly 25 trillion miles away from us. Here's a way to try and visualize this staggering scale. Remember how the Sun is 93 million miles from Earth. Proxima Centauri is about 268,000 times farther away than the Sun. If the distance from Earth to the Sun was represented by just 1 inch, then the distance to Proxima Centauri would be approximately 4 miles. The Voyager 1 spacecraft, launched way back in 1977, is currently the most distant human-made object. It has been traveling for over 47 years and is now about 15 billion miles from Earth, moving at speeds of about 38,000 miles per hour. At that incredible speed, Voyager would still require 73,000 years to reach Proxima Centauri. And it's not even aimed in that direction. Even with truly hypothetical future technology, if we could construct a spacecraft that traveled at 10% the speed of light, which is vastly beyond anything we can currently achieve, it would still take over 42 years to reach Proxima Centauri. The distances between stars are genuinely almost incomprehensibly vast. And here's the thing to remember: Proxima Centauri is our closest stellar neighbor. Most other stars are located much, much farther away. Sirius, the brightest star we see in our night sky, is about 8.6 light-years distant. Betelgeuse, the prominent red giant in the constellation Orion, is roughly 700 light-years away. And even these are considered relatively nearby by cosmic standards. At these monumental scales, Earth doesn't just shrink, it completely vanishes. If you were standing on a planet orbiting Proxima Centauri, looking back toward our solar system, you wouldn't be able to discern Earth at all. Even with a powerful telescope, our Sun would be visible as a bright, distant star, but Earth would be utterly lost in its glare, a tiny dot far too close and too faint to be detected. Let me tell you a little more about Proxima Centauri to help you grasp what it means to be at our nearest star. Proxima Centauri is classified as a red dwarf, which is the most common type of star found throughout our galaxy. It is significantly smaller and cooler than our Sun. Its diameter is only about 129,000 miles, which is roughly 14% of the Sun's diameter. It possesses only about 12% of the Sun's mass. Because Proxima Centauri is so small and cool, it consumes its nuclear fuel very slowly. It is projected to continue shining steadily for trillions of years, long after our Sun has finally died. In fact, no red dwarf star anywhere in the universe has ever died of old age. The universe simply isn't ancient enough yet for that to have occurred. Every red dwarf that has ever formed is still glowing today. Proxima Centauri is also known as a flare star. It regularly produces powerful flares, which are sudden, intense releases of energy that can temporarily increase its brightness dramatically. These flares would be devastating for any planets hoping to host life. The intense radiation from such a flare could strip away a planet's atmosphere or completely sterilize its surface. Interestingly, Proxima Centauri does have at least 2 known planets. Proxima Centauri b orbits within the star's habitable zone, the region where liquid water could potentially exist on a planet's surface. However, given the star's frequent flares and intense radiation, the prospect of life there seems quite unlikely. Still, it's fascinating that the nearest star to us also hosts a planetary system. Proxima Centauri is actually part of a triple star system, gravitationally bound with Alpha Centauri A and Alpha Centauri B. All 3 stars are interconnected, forming a single, complex system. The Alpha Centauri system has captivated and fascinated people for generations, inspiring countless stories and scientific speculation. In reality, we currently possess no technology that could transport humans there within a single human lifetime. Beyond Alpha Centauri, the next closest star is Barnard's star, located about 6 light-years away. Sirius, the brightest star in Earth's night sky, is approximately 8.6 light-years distant. Betelgeuse, one of the most famous stars in our celestial sphere, is about 700 light-years away. It's a red supergiant, so incredibly massive that if you were to place it where our Sun is, it would extend far past the orbit of Mars, swallowing the inner planets whole. All these stars form part of what we consider our immediate stellar neighborhood. And yet, the distances separating us from them are so vast that we will likely never actually visit them with current or near future technology. The light you see when you gaze at Betelgeuse tonight left that star around the time the Crusades were drawing to a close on Earth. And our planet, at these incredible distances, Earth has utterly disappeared from view. The entire solar system itself is reduced to a mere point of light, and Earth is far too small and too faint to be discernible within that tiny point. Let's zoom out even further. All the stars we can observe with our unaided eyes, every single one of them, belongs to our own galaxy, the Milky Way. The Milky Way is a majestic barred spiral galaxy, containing somewhere between 100 billion and 400 billion stars. Our Sun is just one solitary star among this unimaginable multitude. The Milky Way stretches approximately 100,000 light-years across. Remember, Proxima Centauri is about 4.24 light-years away. The sheer width of our galaxy is about 24,000 times that distance. If the distance to Proxima Centauri was just 1 inch, then the Milky Way would be approximately 2,000 feet across. That's taller than most skyscrapers we see in our cities. Our Sun is positioned roughly 26,000 light-years from the very center of the galaxy. We reside in a smaller, less prominent spiral arm, often called the Orion Spur, situated about halfway out from the galactic core. We're not in any particularly special or central location. Rather, we're in what you might call the galactic suburbs, a relatively calm and quiet area where stars aren't too densely packed together. At this immense scale, Earth's presence in the grand cosmos undergoes a conceptual transformation. Even our entire solar system is reduced to nothing more than a minuscule point. The Sun, which seemed so overwhelmingly massive when compared to Earth, is now just one ordinary star among hundreds of billions. And Earth itself. Earth is far too small to even register. Imagine compressing our entire galaxy into a physical structure that is 100 feet across. In this model, our entire solar system would measure thinner than the width of a single human hair. And Earth would be far, far smaller than that. At this scale, Earth wouldn't just be invisible, it would be smaller than an individual atom within the model. The Milky Way is classified as a barred spiral galaxy. This means it possesses a prominent bar-shaped structure at its center, composed of densely packed stars, with elegant spiral arms extending outwards from the ends of this central bar. Our Sun is located within the Orion Spur, which is actually a minor arm that serves as a connector between two much larger spiral arms, known as the Sagittarius arm and the Perseus arm. The galaxy rotates, but it doesn't spin like a solid, rigid wheel. Different regions rotate at varying speeds. Closer to the galactic center, stars complete their orbits at a faster pace. Farther out, like our own solar system, stars orbit more slowly. Our Sun takes an astonishing 225 million years to complete, just one full orbit around the galactic center. This period is referred to as a galactic year or a cosmic year. Take a moment to truly consider that immense span of time. In the duration it takes for our Sun to circle the galaxy once, entire species rise, flourish, and then vanish from the face of Earth. The last time our Sun was at its current point in its orbit, dinosaurs were only just beginning to emerge on our planet. The time before that, the ancient supercontinent Pangaea was still a single, massive landmass. Earth has existed for approximately 20 galactic years. The universe itself has been in existence for about 60 galactic years. These timescales are almost beyond human comprehension. The Milky Way is not a uniform structure, it has several distinct regions. At its very heart lies the galactic bulge, a dense concentration of older stars. This region spans about 10,000 light-years across. The stars here are packed together far more densely than they are in our own neighborhood. If you were to live on a planet situated near the galactic center, your night sky would be ablaze with thousands of incredibly bright stars, making the night almost as luminous as twilight on Earth. At the precise center of this galactic bulge resides Sagittarius A, the supermassive black hole. We'll delve into more detail about this fascinating object later. This black hole possesses a mass equivalent to approximately 4 million times the mass of our Sun. It is relatively quiet now, but it occasionally flares up dramatically when gas, or even an unlucky star, falls into its powerful gravitational grasp. Surrounding the galactic center are the magnificent spiral arms. These are regions where gas and dust are compressed, acting as cosmic nurseries that trigger intense star formation. The spiral arms appear brilliantly bright because they contain numerous young, hot, blue stars. These massive stars live fast and die young, rarely surviving for more than a few million years. By the time they reach the end of their lives, they have barely moved from their birthplace, thus remaining within the spiral arms. Our Sun, being an older, more stable star, has had ample time to drift away from the spiral arm where it originally formed. We are now situated between spiral arms in a comparatively calm region of the galaxy. This is likely a very good thing for life on Earth. Spiral arms are often violent places, characterized by frequent supernovae and intense radiation. Being positioned between these arms provides Earth with a much safer and more stable environment. Enveloping the entire spiral structure is the galactic halo, a roughly spherical region containing ancient stars and numerous globular clusters. The halo extends about 130,000 light-years from the galactic center. The stars found within the halo are among the oldest in the galaxy, having formed when the Milky Way was just beginning to take shape. The halo also contains dark matter. We cannot directly observe dark matter, but we can detect its profound gravitational effects. The Milky Way's dark matter halo extends even farther than the visible stellar halo, potentially reaching out to 600,000 light-years or more. The majority of the Milky Way's mass is actually composed of this mysterious dark matter, not the stars and gas we can readily observe. The Milky Way does not exist in isolation. It is accompanied by numerous satellite galaxies that orbit it. The two most famous of these are the Large and Small Magellanic Clouds. Both of these dwarf galaxies are being slowly torn apart by the Milky Way's immense gravity and will, over billions of years, eventually be completely absorbed into our own galaxy. There are dozens of other, even smaller satellite galaxies. Most are tiny dwarf galaxies, containing only a few million stars. These satellite galaxies are crucial for understanding how larger galaxies grow and evolve. Massive galaxies like the Milky Way are believed to form through a process of mergers, gradually accreting smaller galaxies over cosmic timescales. The satellites we observe today are simply the remaining remnants that have not yet merged. The Milky Way is also actively moving through space, on a collision course with the Andromeda Galaxy. In approximately 4.5 billion years, these two colossal galaxies will merge into a single, much larger elliptical galaxy, eventually containing roughly 1.5 trillion stars in total. Don't worry about the collision itself. When galaxies merge, the stars within them are so incredibly far apart that actual collisions between individual stars are exceptionally rare events. Instead, the galaxies will pass through each other, their mutual gravity slowly pulling them back together until they eventually settle into a single, unified elliptical galaxy. By that distant time, our Sun will likely have already completed its life cycle and be dead anyway. So, humanity, if we still exist, will have long since departed Earth or simply won't be around to witness this spectacular cosmic event. The next largest member of our local group of galaxies is Triangulum, also known as M33. It contains about 40 billion stars and is approximately 60,000 light-years across. It is smaller than the Milky Way, but still a respectable and significant galaxy in its own right. The remaining members of the local group consist mostly of dwarf galaxies. These are small collections of only a few billion stars or even less. The Large Magellanic Cloud, which orbits the Milky Way, contains about 10 billion stars. The Small Magellanic Cloud has a few billion. Both are visible from the southern hemisphere as faint, fuzzy patches in the night sky. The local group, our immediate cosmic neighborhood, spans about 10 million light-years. That sounds absolutely enormous, and it certainly is. But it's just the very beginning of understanding the universe's true scale. The local group is merely one small collection of galaxies within a much larger structure. The local group is in fact part of the Virgo supercluster, an enormous collection of galaxy groups and clusters that stretches across approximately 110 million light-years. The Virgo supercluster contains at least 100 galaxy clusters and groups, with a combined total of somewhere around 100 trillion stars. The dominant structure within the Virgo supercluster is the Virgo cluster itself. This immense cluster is located about 4 million light-years from us and contains anywhere between 1,200 and 2,000 galaxies. Some of these galaxies are truly colossal, far larger even than our own Milky Way. M87, a giant elliptical galaxy situated at the very heart of the Virgo cluster, contains an estimated 1 trillion stars. It measures roughly 120,000 light-years across, similar in diameter to the Milky Way, but it is far more massive. M87 is also famous for being the first galaxy where we directly imaged a black hole. In 2019, the Event Horizon Telescope collaboration released a groundbreaking image showing the shadow of M87's supermassive black hole, which possesses a mass approximately 6.5 billion times the mass of our Sun. Consider this staggering magnitude for a moment. The Milky Way, which seemed so overwhelmingly enormous, is just one galaxy within a cluster that contains thousands. And that cluster is merely one component of a supercluster that itself contains hundreds of clusters. If we were to create a scale model where the Milky Way was reduced to the size of a coin, the Virgo supercluster would then be about the size of a large city. Everything you have heard about up to this point, our Sun, our entire solar system, the immense distances between stars, the Milky Way itself, all of that would fit onto a single coin in this conceptual model. And Earth would be far, far smaller than any particle you could possibly perceive with even the most powerful microscope. At this incredible scale, Earth wouldn't just be invisible, it would be smaller than a single atom in our scaled-down model. In 2014, astronomers made an even more astonishing discovery, revealing something even larger than the Virgo supercluster. They found that the Virgo supercluster is simply a small component of an even more massive structure, which they named Laniakea. The name Laniakea originates from Hawaiian, meaning immeasurable heaven. Laniakea is not just a supercluster. It is a supercluster of superclusters. It encompasses approximately 100,000 galaxies, spread across a staggering 520 million light-years. All of these galaxies, including our own Milky Way, are slowly but steadily moving toward the central region of Laniakea, pulled by the combined gravitational force of all that immense mass. The very center of Laniakea, the gravitational focal point toward which everything is flowing, is known as the Great Attractor. This is a region of space with such an enormous gravitational pull that it is actively drawing in thousands of galaxies. The Great Attractor itself is situated behind the plane of the Milky Way from our perspective, meaning that the dust and gas within our own galaxy obscure our direct view of it. For decades, astronomers were aware that something incredibly massive resided there because they could meticulously measure its profound gravitational effects, but they couldn't actually see it directly. Utilizing different wavelengths of light, radio waves, infrared, and X-rays, astronomers have painstakingly pieced together the true nature of the Great Attractor. It is not a single, isolated object, but rather a vast region containing several massive galaxy clusters. The Norma cluster is one of the largest and most prominent structures within that region. However, even the Great Attractor doesn't represent the complete story. Recent observations and analysis suggest there's something even more massive beyond Laniakea, an unseen gravitational force that is pulling Laniakea and everything within it. This is the Shapley supercluster, located about 650 million light-years away. It contains thousands of galaxies and boasts a total mass estimated at around 10,000 trillion times the mass of our Sun. The combined gravitational influence of the Shapley supercluster appears to be exerting a powerful pull on Laniakea, and consequently, on everything contained within it, including our local group and our own Milky Way galaxy. At this monumental scale, the Milky Way has become merely one among 100,000 galaxies within Laniakea. And Earth. Picture the entire observable universe scaled down to the dimensions of Earth. The Milky Way would then shrink to a size far below the atomic scale, and Earth itself would completely cease to exist at any measurable size whatsoever. If Laniakea, this vast supercluster of superclusters, were compressed to match Earth's dimensions, the Milky Way would barely exceed the volume of a single grain of sand, and Earth would vanish completely into quantum scales, beyond any possibility of detection or even conceptualization. When you meticulously map out the distribution of galaxies across the entire universe, a distinct and fascinating pattern emerges. Galaxies are not randomly scattered throughout space. Instead, they cluster together along immense filaments and walls, forming what scientists refer to as the cosmic web. Between these colossal filaments are vast, expansive regions known as voids. This intricate large-scale structure exists because of how the universe has evolved over billions of years. In the very early universe, there were minuscule density fluctuations in the distribution of matter. Some regions were ever so slightly denser than the average, while others were slightly less dense. Over eons, the relentless force of gravity amplified these minute differences. Denser regions attracted even more matter, becoming progressively denser. Conversely, less dense regions gradually lost matter to their more crowded surroundings, eventually expanding into vast, empty voids. The result of this ongoing gravitational dance is the cosmic web we observe today. Filaments of galaxies stretch across hundreds of millions of light-years, encircling and defining the enormous voids that are almost entirely empty of galaxies. Laniakea, which we just discussed, is one such prominent filament within this intricate web. There are many, many others. One of the largest known structures is the Sloan Great Wall, discovered in 2003. This is an immense wall of galaxies, stretching about 1.37 billion light-years across. It contains tens of thousands of galaxies, meticulously arranged in a relatively thin, sheet-like structure. If the Milky Way were the size of a coin, the Sloan Great Wall would stretch for miles and miles. Another truly colossal structure is the Hercules, Corona Borealis Great Wall, which might actually be the largest structure ever discovered in the universe. It extends an astonishing 10 billion light-years across. That's approximately 73% of the radius of the entire observable universe. Structures of this immense size actually pose significant challenges for cosmologists because, according to our current models of the universe's evolution, there shouldn't have been enough time for something this gargantuan to form. It presents a fascinating puzzle that scientists are actively working to solve. Between these monumental structures are the aforementioned voids. The largest known void is the KBC void, spanning about 2 billion light-years across. Inside this incredibly vast void, there are very few galaxies. It's not completely empty, but the density of galaxies within it is dramatically lower than in the surrounding, more clustered regions. If you were somehow positioned in the very center of this void and looked out, the nearest significant galaxy clusters would be about 1 billion light-years away. The universe would appear vastly emptier from that particular vantage point. These voids collectively make up about 80% of the universe's total volume. The overwhelming majority of space is, in fact, empty. The galaxies, superclusters, and filaments occupy only a small fraction of the total volume. The universe is akin to a vast, sprawling ocean with occasional islands of matter scattered throughout its immense expanse. And our world's significance here. Earth sits on one of these tiny islands within a galaxy that is part of a filament in this colossal cosmic web. At the sheer scale of the cosmic web, Earth doesn't just become invisible, it becomes utterly inconceivable. The difference in size between Earth and the cosmic web is so staggeringly vast that human minds truly struggle to grasp it. The observable universe is simply the portion of the universe that we can, in theory, see. It's limited by the finite speed of light and the age of the universe itself. Light from anything farther away than a certain distance simply hasn't had enough time to reach us yet. The universe is estimated to be about 13.8 billion years old. You might intuitively think this means we can see 13.8 billion light-years in every direction. But that's not quite right. The universe has been expanding continuously throughout its entire history. Space itself has been stretching and growing. So, a galaxy that emitted light 13 billion years ago has actually moved much, much farther away during the immense time its light has traveled toward us. The result of this ongoing expansion is that the observable universe is now approximately 93 billion light-years in diameter. That's the absolute maximum distance from which light has had time to reach us, even when accounting for the continuous expansion of space. Within this vast observable universe, astronomers estimate there are about 2 trillion galaxies. Yes, 2 trillion, each containing anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. For a comparative thought, if every single star was represented by a single grain of sand, you would require several Olympic-sized swimming pools just to hold them all. And Earth would be so unimaginably, fundamentally small that no comparison could possibly capture its scale. You could fit so many Earths into the observable universe that the number becomes entirely meaningless. With the observable universe scaled down to Earth's dimensions, the Milky Way would shrink to a size far beneath subatomic particles, and Earth itself would transcend measurability entirely. It would be smaller than the fundamental particles that actually make up atoms. And here's another crucial point. The observable universe is just what we can currently see. The actual universe is almost certainly much, much larger. How much larger? We simply don't know. It might be a few times larger than what we can observe. It might be thousands of times larger. It might even be infinite. If the universe is indeed infinite, then the observable universe, despite its mind-boggling size, is basically nothing. No matter how enormous 93 billion light-years seems, it still represents 0% of infinity. And Earth would be even less significant in an infinite universe than it already is within the observable universe. Some theories in modern physics even suggest that our universe might be just one part of a much grander multiverse, an infinite collection of universes. According to the theory of eternal inflation, the Big Bang wasn't a singular, isolated event, but rather something that happens constantly, creating countless bubble universes that, in turn, spawn even more bubble universes. Our universe, in this model, would be just one tiny bubble in an infinite, ever-expanding foam. Other interpretations of quantum mechanics propose that every time a quantum event has multiple possible outcomes, the universe effectively splits into multiple branches, with each outcome occurring in a different, parallel branch. This would lead to an infinite number of parallel universes, each representing a different possibility. These ideas are, of course, highly speculative. We currently possess no means to observe other universes. So, testing these intricate theories is incredibly difficult, if not impossible with present technology. However, they arise quite naturally from well-established principles of physics, which is precisely why many physicists take them seriously and continue to explore their implications. If the multiverse truly exists, then our entire universe, with its 93 billion light-year diameter and 2 trillion galaxies, is just one single universe among an infinite multitude. And Earth, in this context, becomes even more vanishingly insignificant beyond any conceivable measure. Let's zoom back in for a moment and examine Earth's precise location within our own solar system more carefully. Because even in our immediate cosmic neighborhood, Earth's inherent smallness becomes strikingly clear. Mercury, the planet closest to the Sun, has a diameter of about 3,032 miles. That's only about 38% of Earth's diameter. Mercury's entire volume could fit inside Earth approximately 18 times. Mercury is a tiny, heavily scorched world, its surface temperatures swinging wildly from about 800 degrees Fahrenheit during the day to a frigid -290 degrees at night. Venus is much closer to Earth in terms of its physical size. It has a diameter of about 7,521 miles, which is about 95% of Earth's diameter. Venus is frequently dubbed Earth's sister planet because of this similar size. However, the surface conditions on Venus couldn't be more dramatically different. Its atmosphere is incredibly thick, choked with carbon dioxide. The atmospheric pressure at the surface is about 90 times higher than Earth's, equivalent to the crushing pressure you'd experience 3,000 feet underwater in Earth's oceans. And the average temperature, it's a scorching 900 degrees Fahrenheit. It's so hot, it's capable of melting lead. Mars is notably smaller than Earth, with a diameter of about 4,212 miles. That's approximately 53% of Earth's diameter. Roughly 7 Mars-sized planets could theoretically nest inside Earth's volume. Mars has 2 tiny moons, Phobos and Deimos, which are most likely captured asteroids. Phobos, the larger one, is only about 14 miles across. If you were somehow standing on Phobos, Mars would loom enormously overhead, dominating half the sky as a colossal red sphere. Jupiter is where things truly begin to get large. With a diameter of about 6,881 miles, Jupiter could span about 11 Earths across its diameter. But it's the sheer volume that truly matters here. Jupiter's volume is so immense that 1,321 Earths would barely fill it. Jupiter is so massive that all the other planets combined possess less mass than Jupiter alone. Jupiter has at least 95 known moons. The 4 largest, known as the Galilean moons after Galileo, who first observed them in 1610, are Europa, Ganymede, and Callisto. Ganymede is the largest moon in the entire solar system, even surpassing the planet Mercury in size. It has a diameter of about 3,273 miles. Europa is particularly intriguing because beneath its icy surface, there is very likely a global ocean that might contain twice as much water as all of Earth's oceans combined. Saturn is nearly as large as Jupiter, with a diameter of about 72,367 miles. Saturn could easily swallow 764 Earth-sized worlds within its massive bulk. Saturn has at least 146 known moons. The largest, Titan, has a diameter of about 3,200 miles. Titan is the only moon in the solar system with a thick atmosphere, and it even boasts liquid lakes and seas on its surface. Not water, though, it's far too cold for that. Instead, these lakes are composed of liquid methane and ethane. Uranus has a diameter of about 1,518 miles. The total volume of Uranus is roughly equivalent to 63 planets the size of ours. Uranus is famously tilted on its side, with its axis of rotation lying almost parallel to its orbital plane. This means that for part of its very long orbit, one pole points almost directly toward the Sun, while the other is plunged into complete darkness. Each season on Uranus lasts for approximately 21 Earth years. Neptune, the most distant planet from the Sun, has a diameter of about 30,599 miles. Neptune's interior could accommodate 57 bodies with the mass of Earth. Neptune is characterized by incredibly high winds, with speeds reaching up to 1,200 miles per hour. These are the fastest sustained winds measured on any planet within our solar system. Even within our very own solar system, Earth is undeniably small. Jupiter absolutely dwarfs it. Saturn could comfortably swallow it whole hundreds of times over. And these are just the planets. When we include the Sun, which overwhelmingly dominates the solar system with 99.86% of its total mass, Earth becomes even more minuscule. Our solar system isn't solely comprised of planets. It's also filled with a multitude of moons, asteroids, comets, and countless other smaller celestial bodies. And many of these are themselves smaller than Earth, which further helps us to understand what small truly signifies in this cosmic context. Earth has one moon. Our moon has a diameter of about 2,159 miles, which is about 27% of Earth's diameter. The moon is actually quite large relative to its parent planet. Most moons throughout the solar system are tiny when compared to the planets they orbit. But Earth and the Moon are sometimes accurately described as a double planet system because the Moon is proportionally so substantial. Mars has 2 moons, but they are both incredibly tiny. Phobos, the larger of the two, is only about 14 miles across. Deimos is even smaller, at approximately 7.5 miles. These moons are most likely captured asteroids rather than objects that formed alongside Mars. Jupiter's moon system is particularly impressive. Besides the 4 large Galilean moons, Jupiter possesses dozens of smaller moons. Many of these are less than 6 miles across. Some are probably captured comets or asteroids. The immense gravitational pull of Jupiter is so powerful that it frequently captures passing objects, adding them to its vast collection of satellites. Saturn's moon system is equally fascinating. Besides Titan, which, as we noted, is larger than Mercury, Saturn boasts Enceladus, a small, icy moon about 313 miles in diameter. Enceladus is remarkable because it has geysers at its south pole that shoot plumes of water ice far into space. This phenomenon strongly suggests the presence of a liquid water ocean beneath its icy crust, making Enceladus another prime candidate for potential life in our solar system. The asteroid belt contains thousands of rocky objects. The largest, Ceres, has a diameter of about 588 miles. That's only about 7% of Earth's diameter. Most asteroids are considerably smaller. Vesta, the second largest, is approximately 326 miles across. The majority of asteroids are merely a few miles or even just a few hundred feet across. Beyond Neptune, in the Kuiper belt, there are thousands of icy objects. Pluto, once considered the 9th planet, has a diameter of about 1,473 miles. That's roughly 18.5% of Earth's diameter. Pluto is now classified as a dwarf planet, one of several large objects within the Kuiper belt. All these smaller objects serve as a vivid reminder that Earth, while small compared to the gas giants, is actually one of the larger solid objects in our solar system. Most moons and asteroids are far smaller than Earth. Our planet is a decent-sized rocky world, but in the grander context of the entire universe, even the gas giants themselves are tiny. Since the first exoplanet was officially confirmed in 1992, astronomers have gone on to discover over 5,500 planets orbiting other stars. These incredible discoveries have unveiled an astounding diversity in planetary systems beyond our own. Some exoplanets are truly enormous. Hot Jupiters, for instance, are gas giant planets that orbit extremely close to their parent stars. These planets can be several times more massive than our own Jupiter. HD 189733b, for example, has a mass approximately 13 times that of Jupiter. It orbits so intimately close to its star that its year is only about 3 Earth days long. Other exoplanets are incredibly tiny. Kepler 37b, for instance, is about the size of Earth's moon, with a diameter of only about 2,400 miles. It completes an orbit around its star every 13 days. Some exoplanets are found within their star's habitable zone, the region where liquid water could potentially exist on a planet's surface. Kepler 452b, for example, orbits within its star's habitable zone and is about 60% larger than Earth. It is located approximately 1,800 light-years away. While we will almost certainly never visit it, it's fascinating to know that such potentially Earth-like planets exist out there. The sheer variety of exoplanets we've discovered demonstrates that planetary systems come in an almost infinite array of configurations. Some stars host multiple planets packed tightly together. Others have planets in highly elliptical orbits, creating dramatic seasonal changes. Some planets even orbit binary star systems, enjoying the spectacle of two suns in their sky. The diversity is truly stunning. But here's what truly matters for our ongoing discussion: Earth is just one planet among the thousands we've already discovered, and likely billions that exist within the Milky Way galaxy alone. Earth is not unique in simply being a planet. It's not even unique in being a rocky planet of roughly our size. There are probably millions or even billions of Earth-sized rocky planets scattered throughout the Milky Way. What might truly be unique about Earth is that it harbors life. As far as we currently know, Earth is the only planet where life, in any form, definitely exists. We might, in time, discover microbial life elsewhere in our own solar system, perhaps beneath the surface of Mars or within the vast subsurface oceans of Europa or Enceladus. And there might be countless other planets teeming with life elsewhere in our galaxy or the wider universe. But right now, Earth stands as the sole confirmed example. This singular fact makes Earth incredibly precious, regardless of its small physical size. Size isn't the only measure of importance. What truly matters is what actually exists on a planet, not merely its dimensions. To further deepen our understanding of Earth's scale, let's turn our attention to stars themselves. Because stars vary enormously in their sizes, and comparing them to Earth places our home world into an even sharper perspective. Our Sun is, as we've noted, a fairly average star. It's what astronomers classify as a G-type main sequence star, often referred to as a yellow dwarf. Its diameter is about 864,000 miles. Approximately 109 Earths could span the Sun's diameter, and an astonishing 1.3 million Earth-sized spheres could comfortably fill its immense volume. However, many stars are considerably smaller than our Sun. Red dwarfs are the most common type of star in the galaxy, as we discussed earlier. Proxima Centauri, the nearest star to us, is a red dwarf with a diameter of about 129,000 miles. That's only about 15% of the Sun's diameter. Roughly 8.5 Earths could be lined up across Proxima Centauri's diameter. The smallest known star is EBLM J055557 AB, with a diameter of approximately 68,000 miles. That's only about 8% of the Sun's diameter. This star is barely large enough to sustain hydrogen fusion in its core. Any smaller, and it would be classified as a brown dwarf, a failed star that never accumulated enough mass and pressure to ignite and sustain nuclear fusion. On the opposite end of the stellar scale are the true giants and hypergiants. Betelgeuse, a red supergiant in the constellation Orion, boasts a diameter of about 617 million miles. That's roughly 700 times larger than our Sun. If you were to hypothetically place Betelgeuse where our Sun is, its outer layers would extend far past the orbit of Mars. Earth would be deep inside the star, instantly vaporized and utterly consumed. But Betelgeuse isn't even the largest. Uy-Scuti, one of the largest known stars, has an absolutely staggering diameter of about 1.7 billion miles. That's approximately 1,900 times larger than the Sun. If Uy-Scuti replaced our Sun, its outer atmosphere would extend past the orbit of Saturn. This stellar giant's volume is so staggering that approximately 6.5 trillion Earth-sized spheres could occupy the same space. That number is so astronomically large it almost loses all meaning. These comparisons vividly demonstrate that Earth isn't just small when compared to the Sun. It's absolutely tiny when measured against even modest stars and becomes incomprehensibly minuscule when compared to the very largest stars. A red dwarf, which is considered a small star, is still enormously larger than Earth. Uy-Scuti is so dramatically larger than Earth that the comparison itself borders on the absurd. When stars eventually exhaust their nuclear fuel and die, they leave behind fascinating remnants. These remnants are often incredibly small but possess astonishing densities. Examining these compact objects provides us with yet another profound perspective on Earth's true scale. When a star similar in mass to our Sun reaches the end of its life, it first swells into a red giant, then gently sheds its outer layers, leaving behind a white dwarf. A white dwarf is essentially the exposed, incredibly dense core of the former star. It is still extremely hot, but much, much smaller. A typical white dwarf has a diameter of about 6,200 miles, which is only about 80% of Earth's diameter. But here's the truly remarkable aspect. Even though a white dwarf is similar in physical size to Earth, it contains approximately half the mass of our Sun. All that incredible mass is compressed into an Earth-sized volume. The resulting density is about 1 million times the density of Earth. To put that into tangible images, a single teaspoon of white dwarf material would weigh an astonishing 5 tons here on Earth. When more massive stars exhaust their fuel and undergo a spectacular supernova explosion, they can leave behind neutron stars. These remnants are even more extreme. A neutron star might be only about 12 miles across, roughly the size of a small city, yet it contains between 1.4 and 2 times the mass of our Sun. The density is so utterly extreme that a single teaspoon of neutron star material would weigh an unimaginable 4 billion tons. The most massive stars, upon their demise, can collapse further into black holes. These are regions of space-time where gravity is so overwhelmingly strong that nothing, not even light itself, can escape their grasp. The supermassive black hole at the center of our Milky Way, Sagittarius A, has a mass about 4 million times that of our Sun. Yet, its event horizon, the boundary beyond which nothing can escape, is only about 17 times the diameter of the Sun. That's incredibly tiny for something so immensely massive. M87's black hole, which was famously imaged in 2019, has a mass about 6.5 billion times the mass of the Sun. Its event horizon is about 3.6 billion miles across. That's enormous. Roughly 250 times the distance from the Sun to Earth. But it is still minuscule compared to the vast galaxy it resides within. These stellar remnants powerfully demonstrate that size and mass do not always directly correlate in the cosmos. A white dwarf is physically smaller than Earth, yet it is far more massive than the Sun. A neutron star is merely the size of a city, but it contains more mass than our Sun. These objects are dense beyond anything we encounter in our everyday lives. But they also serve to remind us that Earth, even though it's small on a cosmic scale, is actually quite substantial for a solid object. Most solid objects in the universe are smaller than Earth. Moons, asteroids, and most stellar remnants tend to be smaller. Earth is a medium-sized rocky planet, and that's actually quite significant in the grand scheme of things. We've talked extensively about the Milky Way, but let's now look more closely at the incredible range of galaxy sizes, because galaxies themselves vary enormously. And understanding this helps us to fully grasp where our Milky Way fits, which, in turn, helps us understand where Earth fits within that context. Dwarf galaxies are by far the most common type of galaxy. These contain anywhere from a few million to a few billion stars and are typically only a few thousand light-years across. The Large Magellanic Cloud, which orbits the Milky Way, contains about 10 billion stars and is roughly 14,000 light-years across. The Small Magellanic Cloud is even smaller. Ultra-faint dwarf galaxies are the very smallest galaxies known. Cygni 1, for example, contains only about 1,000 stars and is a few hundred light-years across. It's barely a galaxy at all. It's more akin to a very large, loosely bound star cluster. These tiny galaxies are ubiquitous throughout the universe. Every large galaxy is surrounded by dozens or even hundreds of these small satellite galaxies. The Milky Way has about 50 known satellites. Andromeda has similar numbers. These small galaxies are considered the leftover building blocks from the early stages of galaxy formation. In the young universe, the first galaxies were all small. Over cosmic time, they merged and accreted to form the larger galaxies we observe today. On the complete opposite end of the scale are the truly colossal giant elliptical galaxies. IC 1101, for instance, is approximately 6 million light-years across, making it 60 times larger than the Milky Way. It contains an estimated 100 trillion stars. This gargantuan galaxy grew by relentlessly consuming and merging with other galaxies over billions of years. It typically resides at the very center of a galaxy cluster, where its immense gravity allows it to cannibalize its neighbors. M87 is another prominent giant elliptical galaxy, about 120,000 light-years across. It's similar in diameter to the Milky Way, but far more massive. It contains about 1 trillion stars and hosts a supermassive black hole at its center with a staggering mass of 6.5 billion solar masses. These giant galaxies are, however, quite rare. Most galaxies in the universe are in fact dwarfs. The Milky Way, with its 100,000 light-year diameter and hundreds of billions of stars, is actually in the top 5% of galaxies by size. Approximately 95% of all galaxies are smaller than the Milky Way. So, while the Milky Way is certainly large by cosmic standards, it is still utterly dwarfed by the very largest galaxies. And at the scale of galaxy clusters, superclusters, and the cosmic web, even the largest galaxies themselves become tiny, insignificant pieces within much larger structures. And our planet, in the vast context of galaxies, Earth completely disappears from any meaningful consideration. The Milky Way spans 100,000 light-years across. Earth is about 8,000 miles in diameter. The ratio between these two sizes is so incredibly vast that Earth becomes essentially non-existent at galactic scales. It simply cannot be perceived or measured. Let's shift our perspective once more and contemplate what Earth is fundamentally made of. Because understanding the intricate structure of matter helps us to grasp scale in an entirely different way. Earth, like everything around us, is composed of atoms. An atom is an unimaginably small entity. The diameter of a hydrogen atom, the simplest and most abundant atom in the universe, is about 0.1 nanometers. That's 0.1 billionths of a meter. You could comfortably line up approximately 10 million hydrogen atoms across the width of a single human hair. How many atoms, then, are contained within Earth? Our planet has a total mass of about 6 trillion kilograms. Most of that immense mass is in the form of iron, oxygen, silicon, magnesium, and various other elements. If we assume an average atomic mass, Earth contains roughly 1.3 multiplied by 10 to the power of 50 atoms. That's a staggering 13 followed by 49 zeros. This number is so incredibly large, it's virtually incomprehensible. If you were to count one atom per second, it would take you more than 10 times the age of the entire universe to count all the atoms in Earth. And remember, Earth is just one relatively small planet. Imagine how many atoms are contained within our Sun, which is over 300,000 times more massive than Earth, or within the Milky Way galaxy, or within the entirety of the observable universe. Atoms themselves possess an intricate internal structure. At the very heart of an atom is a nucleus, composed of protons and neutrons. This nucleus is incredibly tiny, approximately 100,000 times smaller than the atom itself. If a typical atom were expanded to the size of a vast football stadium, the nucleus would be no larger than a marble resting at the precise center of the field. Despite its minuscule size, the nucleus contains almost all of the atom's mass. Protons and neutrons are about 1,800 times more massive than electrons. So, even though electrons occupy the vast majority of the atom's volume, they contribute very little to its overall mass. Protons and neutrons are, in turn, composed of even smaller particles called quarks. 3 quarks combine to form either a proton or a neutron. As far as our current understanding of physics goes, quarks are considered fundamental particles. They are not believed to be made of anything smaller. The crucial takeaway from all of this is that matter, including our planet Earth, possesses structure across an astonishing range of different scales. Atoms are built from nuclei and electrons. Nuclei are built from protons and neutrons, and protons and neutrons are built from quarks. And at every single one of these scales, there is predominantly empty space. An atom, despite its solid appearance, is mostly empty space between its tiny nucleus and its orbiting electrons. If you could somehow remove all the empty space from atoms, if you could compress Earth so that all its constituent atoms were touching nucleus to nucleus, the most of that mass is in the form of iron, oxygen, silicon, magnesium, and other common elements. If we assume an average atomic mass, Earth contains roughly 1.3 multiplied by 10 to the power of 50 atoms. That's a 13 followed by 40, 9 zeros. This is an incomprehensibly vast number. If you attempted to count one atom per second, it would take you more than 10 times the entire age of the universe to count all the atoms in Earth. And Earth is just one single planet. Imagine the sheer number of atoms in the Sun, which is over 300,000 times more massive than Earth, or in the entirety of the Milky Way, or indeed, in the vast expanse of the observable universe. Atoms themselves possess intricate internal structure. At the very center of an atom is a nucleus, which is made up of protons and neutrons. The nucleus is incredibly tiny, about 100,000 times smaller than the atom itself. If an atom were conceptually scaled up to the size of a large football stadium, the nucleus would be no larger than a marble resting at the very center of the field. Despite its minuscule size, the nucleus contains almost all of the atom's mass. Protons and neutrons are approximately 1,800 times more massive than electrons. So, even though electrons occupy most of the atom's volume, they contribute very little to its overall mass. Protons and neutrons are themselves composed of even more fundamental particles called quarks. 3 quarks combine to form either a proton or a neutron. Quarks are, as far as we currently understand, fundamental particles. They are not made of anything smaller. The crucial point of all this is that matter, including our Earth, possesses structure at many incredibly different scales. Atoms are built from nuclei and electrons. Nuclei are constructed from protons and neutrons, and protons and neutrons are, in turn, made of quarks. And at each of these scales, there is predominantly empty space. An atom is overwhelmingly empty space between its nucleus and its orbiting electrons. If you could hypothetically remove all the empty space from atoms, if you could compress Earth so that all its atoms were touching nucleus to nucleus, Earth would shrink to about the size of a large building. All the matter in Earth, compressed to the density of an atomic nucleus, would fit into a sphere approximately 600 feet across. That's still a significant amount of material, but it is minuscule when compared to Earth's actual 8,000-mile diameter. This thought experiment vividly demonstrates that even seemingly solid objects like Earth are, in fact, mostly empty space. The same principle holds true throughout the entire universe. Stars, planets, galaxies. Everything is, in essence, mostly empty space. The universe is far, far emptier than it appears to our senses. Let's introduce yet another dimension to our understanding of Earth's scale, not just how expansive it is in space, but how long it has existed in time. Earth formed approximately 4.54 billion years ago, coalescing from the same swirling disk of gas and dust that gave rise to the Sun and the rest of our solar system. The early Earth was a molten, fiery ball, relentlessly bombarded by a ceaseless barrage of asteroids and comets. Over vast stretches of time, it gradually cooled, developed a solid crust, and eventually acquired an atmosphere and the vast oceans that define it today. Life emerged relatively quickly after Earth became a habitable world. The oldest definitive evidence of life dates back about 3.8 billion years. These were incredibly simple, single-celled organisms, strikingly similar to modern bacteria. For the vast majority of Earth's history, life consisted solely of these simple forms. Complex multicellular life did not make its appearance until about 600 million years ago. The Cambrian explosion, occurring roughly 540 million years ago, witnessed a rapid and dramatic diversification of life forms, giving rise to many of the basic body plans we see today. Since then, life has evolved through countless forms and extinctions. Dinosaurs, for instance, first appeared about 230 million years ago and famously went extinct about 66 million years ago. Humans, our own species, appeared only about 300,000 years ago. If you were to compress Earth's entire 4.54 billion year history into a single calendar year, with January 1st marking Earth's formation and December 31st representing today, then life would first appear in March. The spectacular Cambrian explosion would occur in mid-November. Dinosaurs would make their debut on December 13th and then vanish on December 26th. Humans, by this scale, would only appear at 11:56 p.m. on December 31st. All of recorded human history, everything we've ever built and learned, would occupy merely the last 10 seconds of that entire year. But let's expand our temporal perspective even further. The universe itself is estimated to be about 13.8 billion years old. Earth formed approximately 9.3 billion years after the Big Bang. So, our planet has existed for only about 33% of the universe's total history. The universe is roughly 3 times older than Earth, and the universe has an incredibly long future stretching ahead of it. Current evidence strongly suggests the universe will continue expanding indefinitely, forever. Stars will continue to form for trillions of years, though the rate of star formation will gradually decline over immense stretches of time. Eventually, in about 100 trillion years, all the available gas in galaxies will be used up, and star formation will cease entirely. The universe will then enter what scientists call the degenerate era, where the only sources of light will be the incredibly long-lived red dwarf stars and slowly cooling white dwarfs. Even these will eventually fade into darkness,